to another Project 45 video. In this video, we're going to be looking at motion graphs. It's a topic in A.1 Kinematics. So just quickly, what do I mean by motion graphs? Motion graphs are just graphs of our kinematic variables that we looked at in the previous lesson. If you haven't seen that, definitely go and watch that. So it's things like acceleration, velocity, displacement, time, and speed. They have the same symbol. This can also be d. That's all explained in the previous lesson, so go back and watch that. Today we're just going to be looking at graphs and how these variables are related graphically, and these questions come up a lot and they're pretty easy marks that you can pick up, so you definitely need to make sure that you're super confident with these concepts. Okay, so there's three main graphs that we need to know about. The first is the displacement time graph. So these graphs, as I go through them, they're really going to test your conceptual understanding of these variables and how they actually work in the real world. So yeah, so I'll just go through this graph and explain all the different features. So I've done it in a bunch of different colors to show you the different parts and the distinct parts that you need to know what they mean. So for the displacement time graph, first of all, of course, you have displacement on your y-axis and time on your x-axis. So all three of the graphs that you know, and basically all the graphs that you're going to study for A.1 Kinematics will all have time on the x-axis, and we're just going to change what's on the y-axis. Okay, so first things first is let's see where this graph starts. So of course it starts at this point right here. And at this point, if you think about it, time is 0, so t equals 0, and s equals 0. So what that tells us is the displacement is 0 when t equals 0. So that's our, you can think of it like a starting point, okay? Then after that point, we get this slope, this the line in pink. And what this basically tells us is that the object has started to move. Why? Because if you think about it, as time is increasing, say this is 1 second, we go up from here and we go across to here, say this is 1 meter. So in 1 second, we've moved a meter. So we're moving now. And therefore, we must have a speed. And that's what this line shows us. Since we're increasing our displacement at a constant rate compared to time, since it's a straight line, and the gradient is constant, we have a constant velocity. And remember here, you're definitely going to be saying velocity, since we're using displacement time. You can also have a distance time graph, and in that case, it would be speed. But for this case right here, obviously it's displacement, so it's velocity. And if we go back to the formula for velocity, that's v equals d over t or s, d slash s. It can be displacement, can have s or t. So what this basically tells us is that velocity is the rate of change of displacement with respect to time. So if we look at this pink part of our graph right here, and we can actually calculate the gradient of this pink part. So say at this point the time is 5 seconds have passed, and my displacement right here is 10. So do a bit of basic math. We do rise over run. Our rise is 10, so our run is 5, so our gradient is 2. In other words, what we've just done right here is 10 is the displacement, 5 is the time, so we've done d over t, which is speed or velocity in this case, since it's displacement. So we have 2 meters per second, and the thing that you need to recognize is that it's always 2 meters per second. Why? Because the gradient is the same here, it's the same here, it's the same here, it's the same here, here, on every point along that line. So when we have a straight line that's diagonal or up on a displacement time graph, we have a constant velocity. So let me just label that here. So all the pink parts on this line are constant velocity. Okay, now let's just look at the other two pink parts. So this one, it's the exact same thing. It's a constant velocity. We can do rise over run, calculate the gradient. It's all the same thing. The only difference we have here now is that, well, two main differences. One is that our gradient this time is going to be negative because this graph is sloping down. And that's okay, because that's something that velocity can do. Since it's a vector quantity, it can be negative. So say our gradient here is minus, since it is steeper, we're going to have a bigger value. Say it's minus 5 meters per second. that means we're going minus 5 meters per second in the opposite direction, right? And that makes sense as well, since if we look at our displacement, if we just draw across our displacement from here, let me use a different color actually. Let's go for yellow. Okay, so if we go to here, we start at 10, and then when we end, I'm looking at this pink line here, this one, the one that I've now made yellow, and we go across to here. Our displacement has actually gone down from 10 to whatever this value is here. Let's give it something like 3. And that makes sense because we're going backwards since our velocity is negative, so our displacement is decreasing. Because remember, at s equals 0 or displacement equals 0, that's our starting point. So we've gone forward from that, which is a pink line. Then there's that blue bit. I'll discuss the blue bit in a second. And then we've gone backwards. Our velocity has changed. We haven't gotten all the way back, but we're somewhere on our way back. Okay, let me just clear away some of these annotations now before we move on. Okay, so now let's move on to the blue parts of our graph. So we have 2 blue parts, one here and here. So these are pretty simple. It just means that the object isn't moving or it's at rest. So I'll just write that out over here. Blue is at rest. It's pretty obvious. It just means it's not moving, right? We can see that on the graph since time is increasing. So let me just do something like this. We're going from here to here, right? So say this is 6 seconds and this is 9 seconds. So over 3 seconds, our displacement is staying the exact same, like it's not moving. What was this? We called it 10 before. Yeah. So our displacement is staying 10, so we're just staying in the same position. If you're staying in the same position, you're not moving. So yeah, exact same thing on the other blue part over here. Just we're staying in the same position at a different position over a different length of time, since it's slightly shorter. So I think this is roughly 2 seconds across. So in 2 seconds, we're just saying whatever we want to call this for, probably closer to 3. Yeah, I think we did label it 3 before. Let's keep it 3. So we're just saying at 3 meters of displacement. So again, we're not moving. So the blue part's pretty simple. One thing you will definitely want to remember though is, like we said before, by calculating the gradient of any part of a displacement time graph, you can do it literally anywhere. You'll find the velocity at that point, which is the instantaneous velocity. Like exactly at that point in time, that's how fast it's going. And for these blue parts, when I calculate my gradient, if you know a bit of math, I hope you do, it's going to be 0, right? So that means v equals 0, and that makes perfect sense because that means we're not moving and we're staying in the same place, so we have 0 velocity. Okay, now the next thing we're going to look at is the green part. So we only have one green part here. And basically, what we're looking at here is a changing gradient. So how can we look at that? Okay, say we have 2 points here along this green part. When we're calculating the gradient of a curved line, you've probably done this in math before. You draw a tangent and then you calculate the gradient of the tangent. So if we draw a tangent here, something like that, it's really steep. But if I draw it here, it's a lot less steep. It's more flat. And what that tells us is that the gradient is actually decreasing. It's getting closer to a flatter line or closer to 0. So what that actually tells us is, since the gradient of a line is the velocity, so here this means we have a high velocity. That did not work. Yep, there we go. We have a high velocity. And then the second line, we have a low velocity, so it's a decrease. So we're having a change in velocity as time passes, right? Because time is passing along the x-axis. And if you have watched the previous video, you'll know that a change in velocity with respect to time is acceleration. So the initial velocity here, which we can call u, and the final velocity here, which we can call v, it's v minus u over t. Same formula for acceleration. So all this curved line shows us is that the object is accelerating. Okay, so I can just put that up here, that the green bits are acceleration, since velocity is changing. And the implications of that are that on the other parts of the graph, the straight line here, since the velocity is not changing and it's constant, that means no change in velocity. So the change in velocity is 0, which means that acceleration is 0. So that is something you can see from the graphs here. Okay, and the final point for this part of the graph is that since our curve is downwards, there might be too many annotations for you to see it, but it looks like this, right? It has that shape. Since we're starting off at a high velocity and we're going down to a low velocity, that means we're actually slowing down. So you can you can say one of two things. You can say it's either a negative acceleration or it's a deceleration. It's the same thing, right? So you can say negative acceleration, or we also call that a deceleration, which just means slowing down. And when you write okay, let me just pretend like we have values here, so it makes it a bit easier. See a different color. Okay, actually no, yeah. So the negative acceleration, say our acceleration was 3 meters per second squared. We would say 3 meters per second squared minus, it's negative 3 meters per second squared. But if we're saying it decelerated, we don't need to include the negative since we've already said it's decelerating. So yeah, and in this case we wouldn't include the negative either. We just say an acceleration of negative 3 meters per second or a deceleration of 3 meters per second squared, not meters per second. Okay, and now the final thing that we need to know for a displacement time graph is what the area under the graph means. Actually, before that, I will just note, when we're looking at this graph, not all graphs will be like this, but this graph in particular, we can also say that since we started displacement 0, then we're back at displacement 0. Between these two time points, we've actually just come back to the same position. Like say this was our starting point and this is where s equals 0. So then we've gone on this whole path, we've gone all the way here, taken a rest here since the graph goes flat here. Then our velocity goes negative, right? So we've gone backwards, and we've taken another rest, so we pause here, and then we decelerate and get down to here, right? So, and that actually happens again later on in the graph. We go from point 0 again to point 0 over here. So exact same thing. We've just, and this time, what you might want to know is that since it's under the x-axis, the displacement values here are actually negative. So if I go across from here, this line right here, it'll be something like -2 meters, something like that. That just means like since before we were going outwards and backwards and this towards the right, in this case now we're going out and back from the left. And again, this is something that applies across all of physics. In terms of direction, you just choose one direction if it's not stated in the question. And then the opposite direction is negative, and as long as you keep that constant throughout your calculations, you won't get it wrong. Okay, now the final thing that we need to know is what the area under the graph actually means. Now for this particular graph, it means nothing. Why? Because if we're calculating the area of any particular point, like say I box off this section right here, what I'm doing is I'm doing the displacement times time, because my x-axis here is a value of t and my length of this rectangle is a value of s, so my area is s times t, and displacement times time has no real meaning, so it's meaningless. And I've seen a lot of questions actually have come up on this before. Many people know what the areas of different graphs mean, which we will also look at. But a lot of the time they forget that they also need to know that this area under a displacement time graph means nothing. So yeah, definitely make sure you know that. Alright, now that graph took us a while to go through since I was just going through explaining all the features. This one hopefully should be quicker. So our second graph is the velocity time graph. Again, same scenario here. You got velocity on the y-axis and time on the x-axis. The graph shape I've used is the exact same since it has all the different features like straight lines, flat lines, and curved lines. But obviously it means very different things, so don't get mixed up with that. Okay, same scenario. This time, we need to be mindful that we have velocity and not displacement. So a straight line, this pink part, let me change my color to a matching color. The pink part is showing a change in velocity, right? We're starting at 0 velocity and we're going up to whatever value of velocity over a certain amount of time. And if we calculate the gradient of this line, we're actually going to do rise over run. So let me just decide some values. This is obviously 0. Let's make this 5 seconds. And let's make this 10. If you calculate the change in velocity, it's 10 minus 0, which is just 10. And divide that by time, and that'll be 2. So our change in velocity over time is acceleration. So that's 2 meters per second squared. So a straight line means an acceleration on a velocity time graph. And obviously throughout different points on the line, the gradient is always 2, so it's uniform acceleration. So it means the acceleration is staying constant throughout that portion of the line. Same situation here with the other pink line, except it's in the negative direction. So we have a deceleration, since our gradient is going to be negative. And it's the same situation again, uniform acceleration, same deceleration throughout. So I'll just label that over here. The pink parts are uniform acceleration. The uniform part, again, it just means it stays constant, like constant acceleration. Okay, now let's look at the blue parts of the graph. So here, time is changing, but our velocity is staying the exact same, and time is changing. That just means no acceleration. Since the gradient of the graph is acceleration, the gradient of this flat part is 0, so a equals 0, acceleration equals 0, and in other words, we have constant velocity. So let me label that here, constant velocity, or a equals 0, same thing. Okay, and the same thing for the other blue part, it's also just constant velocity, so it's just moving at the same speed. Many people often confuse this with the object stopping, and that's wrong because that's a displacement time graph. That's not for a velocity time graph. For a velocity time graph, when an object is not moving, if you think about that, that means that the velocity has to equal 0. And wherever the velocity equals 0, the object has stopped. So that will be this point here, and this point here. Those are the object places where the object is at rest. So I'll label that in black. It's when the y-axis v equals 0. Put that in commas because there's 2 equals. There you go. V equals 0 is at rest. Okay, now for the green part of the graph. Now this is pretty rare to see in a velocity time graph. Often you're not really assessed on this because you don't really need to know it. But I mean, it's just extra information, you might as well. So all this means is, since a gradient, like we discussed last time, when we have a curve, the gradient is changing consistently. And in this case, our gradient is acceleration. I'll actually write that up here in round color. Gradient is equal to acceleration. Okay, since our gradient is acceleration, and on the green part, the gradient is constantly changing, we have a changing acceleration. You don't need to know what that's called, because it's not part of the course for the IB, but it's called jerk. So I'll use delta actually. So delta A over time. So the change in acceleration over time is equal to this thing called jerk. Yeah, you don't need to know it, just extra information. But yeah, those are all the features of velocity time graph that I've drawn. One final thing is the area. Now this is one of the most commonly assessed features of this graph, is the area under the graph. Now in this case, the area is not meaningless, it does have a meaning. So if I box off this area actually, I'll get a change in time on my x-axis, or the width of this rectangle, and the length of the rectangle is going to be v. And when I have v times time, that gives me displacement. Since the formula for velocity is displacement over time, if I rearrange that, I can get v times t equals s. So the area under the graph is equal to displacement, and that applies for the whole graph. So for example, this triangle here that I've highlighted, you'd use the area of a triangle formula, which is half times the base times the height. And you do that across the entire graph. You can just split it up into little sections like this, split this up into a rectangle. For curved areas, you won't really be asked the area under. You can be, and in that case, whatever grid or graphing paper you're on will have little boxes, something like this. So you just have to figure out what one box represents in terms of area, the area of one box, and then estimate how many boxes fall under your curve, and then give a good estimate. And in the mark schemes, the answer is usually a range, so it should be fine. Okay, now one thing you definitely need to be really careful of when you're doing area under the graph calculations for a velocity time graph is you need to be understanding of the difference between displacement and the difference between distance. So distance, of course, if you've seen that in the last video, if you haven't seen that, again, go and watch that. Distance is a scalar quantity, so we don't care about direction. However, displacement is a vector quantity. So say I started at a starting point here, I went 5 meters forward, and then I came back 3 meters. My distance would be 5 plus 3, which is 8. But my displacement would be only 2 meters, because that's how far I've gone overall from my starting point. So it's only 2 meters. So I've done 5 minus 3. And that's the same idea when you're calculating area. So we have part of the graph that's above the x-axis, so that's all of this part over here. And then we also have, straight in a different color, part of the graph that's below the x-axis. And that means that displacement can be negative, right? So this area is actually a negative area. So say our total area here is minus 3 meters in displacement, and our total here was 10 meters. That's going to be positive. Our total displacement would be 10 minus 3 equals 7 meters overall. And our distance traveled, however, would be 13 meters because we do 10 plus 3. So yeah, just be mindful of that. And of course, the implications on that are that for the yellow part of the graph, the yellow highlighted, we're going in one direction, and for the pink part of the graph, we're going backwards in the opposite direction, back towards our starting point. Okay, now for the acceleration time graph. This is going to be the final graph that you need to know. And again, I've done the same graph shape just because it has all the different features, but of course it means different things. So let's go through that now. First of all, the axes of the graph. We have time on the x-axis as always, and acceleration on the y-axis this time. So the pink part's first. Right, let me change my color. Okay. The pink part shows a changing acceleration. Like I discussed before, a changing acceleration is jerk. Again, you do not need to know this, but you don't need to know the word jerk. You can just say a changing acceleration. It's not really in the course, but it's just extra information. It's good to know it. This part is a flat acceleration, and again, as always, the gradient of the graph will give you the value of the jerk. Let me just do that here. We're going to use the delta symbol that just means change acceleration, which is also jerk. Okay. Now the blue parts of the graph. Okay. The blue parts show a non-changing acceleration, but time is changing. So we have a constant acceleration. A constant acceleration is usually called a uniform acceleration. Okay, and the same thing for the other blue part here. The green part is going to be a change in jerk. So yeah, that's like a change in acceleration. Like a change in velocity is acceleration, a change in acceleration is jerk, and now we have a change in jerk. So that you definitely don't need to know, and it doesn't really mean anything useful. So you can just ignore the green part. The main thing that you're assessed on for an acceleration time graph is the area under the graph. The other sort of parts are not that important for this graph. So let's look at the area. So again, we have a area above and a area below the x-axis. So for the yellow area, let's just discuss what area means, right? You're doing acceleration times time when you calculate the area of the rectangle. It's the same rectangle I always draw. If you look at our formulas, our formula for acceleration is v minus u, change in velocity, over time, equals acceleration. If we rearrange this, we get v minus u equals a times t. And that's why our area under the graph is change in velocity, v minus u. We can just call that delta v. So it's the change in velocity. So say my area under this yellow part of the graph is 20 meters per second. And again, why would we get meters per second? Because our time is in seconds and our acceleration's in meters per second squared. So one of those seconds is going to cancel out to give us just meters per second. That's going to give us 20 meters per second. The purple part is going to give us a negative change in velocity, and that'll be something like minus 5 meters per second. So yeah, you can calculate the overall change in velocity. There's no real use in doing that, but yeah, just something you can recognize. So of course for this part it's decelerating, since all the acceleration values are negative. If I go to any point across, it's going to give me a negative acceleration, negative. So that's deceleration. So this entire part is just slowing down, basically. Slowing down or decelerating. Except for when the gradient goes positive. Like here it does go positive, it's going upwards towards 0, so it is actually accelerating in those parts, but wherever it's going downwards, it's decelerating, since it's negative acceleration. And for the positive part, we have a positive acceleration, so it's just accelerating. Yeah, that's basically all you need to know for this graph. Okay, so now we're going to be looking at the motion of a bouncing ball. This video is becoming really long, but I think all of the stuff in here is worth watching. So yeah, these questions come up super often and they're really easy marks to pick up if you know what you're doing. So the idea here is simple. Just to explain to you how these graphs are interlinked, is we're going to imagine a ball that's just bouncing up and down. It goes down, then it goes up, then down, then up. And we're going to assume that air resistance isn't involved, so it's going to bounce back to the same height, whatever you want to call this, like 10 meters, doesn't really matter, the same height. It's bouncing back up to the same height, and it's on Earth, right? So our acceleration due to gravity is going to be the value of g, which is 9.81 meters per second squared. Okay, so I've drawn 3 graphs here, which are the same graphs that we've just looked at. And as you can see, if you see the gray dashed lines, they're basically showing that these graphs are drawn at the same time, right? This is like, say this 5 seconds in, this is 5 seconds in, and this is 5 seconds in. So it's showing what's going on with the different quantities, displacement, velocity, and acceleration at the same times. Okay, so first let's look at our first graph, this one right here, the displacement time graph. Pretty simple. The ball at, let me use my laser pointer. The ball at 0 seconds has moved 0 distance, bounces up, goes through a displacement. This is the top of the motion. Then it bounces, then it falls down, and then it bounces up at the top of the motion. Then it falls down, then it bounces up, then it falls down. It's just bouncing up and down, right? Yeah, pretty simple. If we look at the velocity now, at the same time, so when the ball is about to bounce, the velocity of the ball will suddenly get a value, because the ball like squeezes when it's on the floor, and then it bounces up really fast, so it accelerates super fast upwards. So there's no like graph for this kind of area. The graph just starts up here. Then the ball slows down as it goes up. That's why we have a negative gradient. And if you look at the acceleration, actually no, we'll look at the acceleration at the end, but it has a negative acceleration since the gradient of the graph is negative. Then it hits 0, and that is at the top of the motion. That is because the ball, as it rises, will slow down, and then when it gets to the top, it'll momentarily stop at the top, and then it will fall back down. So it stops here, falls back down, bounces, and we're back up again, going upwards at the top of the motion. And you can line up the graphs, right, and you can see what's happening. So this is the top of the motion, the velocity is 0 at the top of the motion. And when the ball is falling back towards the ground, just before it hits the ground, our velocity has a value because it's accelerated, gotten faster right before it's about to hit the ground. Now the acceleration graph might look a bit weird if I just zoom in here. That's because the acceleration due to gravity is going to be constant. It's, like I said before, it's always going to be 9.81 meters per second squared. So we just kind of have like a flat line going here, and the flat line is at the value minus 9.81 meters per second squared. So yeah, just constant acceleration. The only thing that you might notice is that these dotted lines going here. Now, to explain this, if you look at what's going on, we see that momentarily when the ball is at the bouncing point, like when it touches the ground, it's about to bounce back up, we have a sudden change in direction of velocity. So since velocity is a vector quantity, a change in the direction of velocity will make it negative or positive. Like say we have minus 5 meters per second, and suddenly we change directions really quickly, which is what happens with a bouncy ball. It's really quickly going to go upwards when it touches the ground. We're suddenly going to move to 5 meters per second, and that momentarily provides a tiny acceleration, which is why the graph kind of like jumps to this point up here for like a split second. But usually that time period is so tiny that even like digital meters and stuff, they don't really recognize it, so it kind of just appears as a graph, as a gap on the graph. So you just have like this kind of gap in the acceleration value that you're recording. That's all it means. Yeah. So that is everything you need to know. The motion of a bouncing ball was just an example to get the graphs lined up and show you how all the different quantities link and how they can be applied. So yeah, next video we're going to be looking at the kinematic equations of motion. So definitely watch that as well. And if you haven't seen the previous video for 8.1 kinematics, also go back and watch that. This was a really long video, but make sure you understand everything super well, since these are really easy marks to pick up in the exam. And if you have any questions, just put them in the comments and we'll try our best to answer as many as we can. Thank you.